Okay, so sphere initially at 0 has its surface kept at 100 from t equals 0. We're going to find the time dependent temperature distribution. And so we are going to be solving the following differential equation. The heat flow equation, d squared u is equal to a squared du over dt. Okay. So that means du over dt. So here's in spherical coordinates, since this is a sphere, we have three variables r, theta, phi. There's symmetry on the theta, so temperature distribution is not affected by a change of this. Neither is phi because of symmetry, so the only one that we use is the r, so we have du over dt is a squared 1 over r squared d over dr in spherical coordinates r squared du over dr. And if we apply the product rule here, we get a squared 1 over r squared 2r du over dr plus r squared d squared u over dr squared. And if we get du over dt equal a squared times 2 over r du over dr plus d squared u over dr squared. No? Okay. How are we doing there? Yeah. So, okay. It's probably easier if we scale the temperature down by 100, so we can apply conditions at 0 instead of 100. So what I will do, I will call I to be u minus 100. So wherever the temperature is 0, it will be minus 100, and whenever it's 100, it will be 0, which would enable me to scale my initial conditions to temperature 0. Okay, and so we're going to be using separation of variables. Of course, 100 is a constant, so the derivatives of I are identical to the derivatives of u. So separation assume solutions of the form I equals t some function of t and r some function of r. We'll take the derivatives. So dt over dt times r of r equals a squared 2 over r t dr over dr plus t d squared r over dr squared. And so now we're going to divide by RT. So if we do that, so divide this whole thing by RT, and we will get 1 over T dt over dt. And I will multiply the R over there, so we have a squared 2 over r 1 over r dr over r dr plus 1 over r d squared r over dr squared. Okay, this is a function of t alone, and this is a function of r alone. So each one has to equal to a constant if they were to be equal. So that means we're going to go to the t equation. Have questions, man? T equation. The Fourier trick is chapter 7. Yeah. I mean, basically, you're not going to find something specifically called Fourier trick. It's just it's just the fact that when you integrate, I showed you this last time. When you integrate, it's just a trick. When you multiply both sides and by sign and integrate, look, whenever these two are the same, the answer is 0, and the only time that you get an answer is when they are the same. So that's the trick. So the t equation, we have 1 over t dt over dt equals, so minus k, I'm going to call this minus k squared as a constant, and then there's an a squared factor, which is here. Now, the reason I do this is because if I call it k squared, the solutions will be exponentials, and as t goes to infinity, the temperature would go to infinity, which does not physically make sense according to the boundary conditions. So it has to be sines and cosines. For it to be sines and cosines, it has to be a negative to make physical sense. So now, so this is just can make those straight derivatives. So we have dt over dt is equal to minus k squared a squared. Separation of variables, t in the dt here, integrate both sides, and so we get ln(t) is equal to minus k squared a squared t plus c. So that means the t equation as a function of t will equal ce to the k squared minus k squared a squared t. So this is the temperature equation. Okay, let's do the R equation. Now that we've got rid of this A, so we have 1 over, so the R equation is, so now we're going to transition to the R equation. So we have d squared r over dr squared plus 2 over r dr over dr is equal to minus k squared r. And if we move everything to the right, this will be, and we scale by r squared, this will become r squared d squared r over dr squared plus 2r plus 2r dr over dr plus k squared r equals 0. This is the BESSEL equation, and the book. This is equation 12.1, page 588. Okay, and the solutions to this are the Bessel functions. So here, Ben, you have questions? P equals 0. And x is kr, according to this equation. So the solutions to Bessel function will be j of 0 to the Bessel equation will be functions j0 kr. This will be the R equation of kr. So this is the first solution. Now there is another solution defined by n, but this solution does not really, because this is a solution does not work because r equals 0 is inside the sphere, and the other solution excludes that. So I think that becomes, because the other solution is over sine 0, I believe. Yeah, so it's something over 0, so excluded. So there's only one solution, so that means R is equal to some constant A times J0 KR. That's the functions. Okay, so now apply the boundary conditions. So apply boundary conditions to this. Okay, so that R at some R0 has to equal 0 according to the boundary conditions. So that means J0 KR0 is equal to 0. These are the zeros of the Bessel function. Now J0 KR0 according to equation uh, section 17.4 is equal to x, n is 0, so this is x2 is 0, minus 1 over x d over dx to the 0, so this whole thing is 1, this is 1, of sine x over x. And this has to equal 0. This is equation 17.4, page 596. Okay, and x is just kr0. So this is, or there's an x, replace it by kr0, so kr0 over kr0. So that means sine kr0 is equal to m pi, which makes k equals m pi over r0. Okay, good. So now we know that our R equation of KR is equal to AM Bessel solutions for the Bessel function at K, which is M pi over R0R, and I will be the product of the two. So I is equal to, now there's a summation, because m is any integer. M can be 1, 2, 3, all the way to infinity. So from m equals 1 to infinity, m equals 0 does not match the boundary conditions. Some coefficient am j0 of m pi over r0 r e to the minus m pi over r0 a squared t. And now the objective is to find this guy. Now I could turn this BESSEL function here into a sine term using the definition 17.4 that I just used. And I will equal, Ben, you have a question? M equals 1 to infinity am sine m pi over r0 r times r0 over m pi r e to the minus m pi over r0 a squared t. Okay, so now probably easier to work with we can use the Fourier trick to determine the coefficients. So
Then we have the extra.
this extra term,
Yeah.
this came from the definition of the BESSEL function that I just used a moment ago. If you plug it into equation 17.4, page 596, you would get an extra term because you don't have an x here. You have m pi over r0. Your x there is m pi r over r0.
Yeah.
And here you have over x, so you're going to get over m pi over r0, sine x over x. Yeah, look, you have sine x over x. So when you divide by m pi over r0, it's the same thing as multiplying by.
Oh, I didn't notice you didn't have that.
R0 over m pi r. You just flip it.
Yeah, I didn't notice that you didn't have that denominator.
Yeah.
Yeah.
So that's where that came from. Okay, so if I do use, oh, no, Fourier trick here is not going to work, and the reason it's not going to work is because we have an r term here. So we do have to work with the BESSEL functions. I don't think, I mean, a similar trick will work, but Fourier trick itself will not work because you have r dependence. And so when you integrate, the answer isn't going to be that. So yeah, we do. So it's probably, so we're going to be using this more than now to figure out the coefficients. Okay, so we're going to be using this. Put stars around it. Okay, well, I know that. What's happening here? I know that I r at 0 is equal to minus 100 because it's at 0, but we scaled down by 100, so the boundary condition became 100. And at t equals 0, if I plug in t equals 0 in the I, that goes away. The e exponential becomes 1, and then I have am. You're working, Ben? You have a question? R0 over m. Oops. Let me use the BESSEL one. J0 m pi over r0 r. Yeah, from m equals 1 to infinity. Okay, and now we will exploit the orthogonality relationship if you don't get that step, then pay attention because I'm there now, so you can see how I use it. But you have to do it.
Yeah.
So I will if you go to page 602 in your book, uh, equation 1911. Okay, this talks about the orthogonality of the Bessel functions. That says equation 1911, page 602. Let's write it out. Okay, 602. So that says right here, 1911. So the integral from 0 to a, generalizing the integral of p alpha r over a, okay, um, then by the way, the alpha and the beta are zeros, are the zeros of the Bessel function jp. So alpha r over a, jp beta r over a dr, this equals 0 if alpha does not equal beta, and it equals a squared over 2 j squared of p plus 1 of alpha, whatever that 0 is. So if I apply this to mine, okay, if I apply this to mine, we know that alpha r over a, it has to equal what's inside my Bessel function m pi over r0 r, which means a has to, if you match this, a has to equal r0 and alpha has to equal m pi according to this. And so now you can, so this is orthogonality here. Orthogonality of Bessel functions. You follow? Yeah, so in this case, m pi over r0 times r has to equal alpha r over a, what's inside the Bessel function here. And reading of this, a has to equal r0 and alpha has to equal m pi. And now just plug them here in what you have. So what I'm going to do, I'm going to multiply both sides of my original, of this equation, by the Bessel function of n pi r over r0. And so I will get, let me change the color here. So 0 to r0, r squared, j0, m pi, over r0 r times j0 m pi n pi over r0 r dr. Yeah, so according to my relation, this equals to so I'm not applying it yet, I'm just writing it out. So this is equals 0 if m does not equal to n, and will equal r0 cube over 2, because I have an additional r factors here. So in the original equation it's r, but if I have r squared, then this becomes r0 cube over 2. The Bessel function of p plus 1, p is 0, so this would be Bessel function of 1 of the zeros of alpha and alpha is m pi according to what we've determined squared. This is if m equals n. Okay, and now I'm going to apply this to I r of 0, which is this equation here. So project on I r of 0. So if I do that, I will get minus 100. And so I'm multiplying both sides by 0 to r0, j0, k pi over r0 r squared dr. Yeah. And also the right hand side, so I multiplied the minus 100 on the left by that, and I will multiply the right hand side also by that. But according to the identity that I wrote in black, the right hand side, all the terms will vanish except where m equals n, and that's going to give me the coefficient ak over 2, right? Or ak times j1 of k pi. I'm just transitioning here from m to pi because I've used k on the left hand side, so I'll just call it k now, squared r0 cube over 2. Okay. So now the question becomes how to evaluate this integral. How to evaluate this integral. Yeah. Well, there's many ways to do it. You could, we know from the recursion relation, page 15, page 592, equation 15.1, it says d over dx, the integral for sine will be difficult. I'll just do it using the recursion relationship. It's easier. So x to the p, jp of x equals xp jp minus 1 of x. Okay, so by the fundamental theorem of calculus, if the derivative of this is this, that means the integral of the right hand side will give you the left hand side. So then the integral of xp jp minus 1 of x has to equal xp jp of x. So that's how we're going to trick this backwards in order to evaluate the integral. So now we're going to use this to evaluate the integral that we got here in green, which is 0 to r0 j0. So this guy is this guy here. So j0 k pi r over r0. You follow, Ben? R squared dr. So I will evaluate this. So watch, I will evaluate this. I will introduce a substitution here. So okay. So let u equals k pi over r0 r, which makes r to equal r0 over k pi u, and dr, if you differentiate this, dr will equal r0 over k pi, this is just a constant, times du. And so plug, oh, and the bounds, we have to change the bounds. So let's do that. So when, so these bounds are for r equals 0 and r equal r0. So when r equals 0, plug it here. you get u equals 0. U equals 0. And when r, this is a separator, when r equal r0, plug it there, r and r0 cancel out, and you get u equals k pi. So now plug back into the integral. So now the integral will run from 0 to k pi j0 of u. So I'm setting up the integral to use the recursion formula after the substitution, u squared gu. Okay, and according to the formula that I wrote here, the recursion formula, this is just u squared j1 of u evaluated from 0, because we were at Bessel function 0, now we're at p equals 1, Bessel function 1, or Bessel's solution for the Bessel function. So 0, and now we can plug in from 0 to 1, so we will get u squared, which is k pi squared j1 of k pi minus u of 0 is 0, and this whole thing is multiplied by there was here a factor of 1 second. Oh yeah, the du. I forgot the factor of u, which turned out to be r0 over k pi cube, because there was originally an r squared. R squared is r0 over k pi squared, and there's another r0 over k pi coming from the gr, so that makes it r0 over k pi cube. So this is r0 cube over k pi cube, and we can cross two of these with two of these, and we have left for this integral r0 cube over k pi Bessel 1 p equals 1 of k pi, which we can find. Bessel of j1 of k pi we can find. I'll find it in a second. So this guy is the answer for the integral that was on the left hand side here. Okay, so now I will go back to this red one here, and I will plug in the answer. So in there, so minus 100. So let's call this equation here A. So plug in A. So we have minus 100. Let's change the color. So minus 100 multiplied by r0 cube over k pi j1 of k pi. So this is the left hand side, and this has to equal, where did it go, ak times j1 of k pi all squared times r0 cube over 2. And we could do some simplifying here. One of these guys goes with one of these. R0 cube cancels R0 cube, and we will get AK to equal minus 200 over K pi times J1 of K pi. Okay, so we found AK. Let's go ahead and figure out what this guy here is. J1 of K pi. So we're gonna again plug it into the equation that we used earlier, which is 17.4, page 596. So J1 of K pi, so X is K pi in that equation, is equal to K pi to the 1, N is 1, or P is 1, depending on which book you're looking at. So minus 1 over k pi d over dx to the 1, so that's the first derivative, of sine x over x. And then when we're done, we evaluate x equals k pi in there. So now I could cross out this with this, and we have left minus let's see, so quotient rule on this, sine x is x cosine x minus sine x over x squared, and we're going to evaluate this at x equals k pi. So this is going to be minus k pi cosine k pi minus sine k pi, right? Sine k pi, of course, is 0. Then you have question over k pi squared and this is of course going to depend, so this is j1 of k pi, so this here will equal well, one of these cancels one of these, so if k is even, we get minus 1 over k pi. Minus 1 over k pi, yeah, because cosine 2 pi, even multiples of pi is 1. This is if k is even. So here k is even. If k is even. And if k is odd, we get 1 over k pi. If k is odd. So we could write this as one equation, which will be j1 of k pi will equal to minus 1 to the k plus 1 over k pi, such that if k is even, we get the negative answer, and if k is odd, we get the positive answer. So this is j1 of k pi, and now we're going to take this and plug it in here in AK. So AK becomes minus 200 over was it minus 200? Yeah, minus 200 over k pi minus 1 to the k plus 1 over k pi. So I could cross out these k pi's, and minus 1 to the k plus 1 is either minus 1 or plus 1, so I can equally likely bring it up to the numerator. So this becomes minus 200 minus 1 to the k plus 1 times minus 1 to the k plus 1. It doesn't matter if it's minus 1 or plus 1, whether it's in the numerator or denominator, it doesn't make a difference. Yeah, so now so this is my AK, of course. This is my AK. So now just plug it in U. So U is basically I could plug it in I, but U is just 100. Where is it? The very beginning. So now I found my I because I found all the coefficients AM. And originally I started by saying I is U minus 100, and the objective is to get to U, not I. So U will be I plus 100. I plus 100. So U, according to this, U will be finally U will be 100. So let's write this in this color. So U of RT, temperature distribution, will be 100 plus U, but there's a minus sign, so minus 200 over pi uh, summation from k equals 1 to infinity minus 1 to the k plus 1. This is the coefficient. Sine k pi over r0 r over kr e to the minus m pi over r0a squared times t. This is the final answer. This U that we obtained, which is the series solution, is the time-dependent temperature distribution in the sphere. Ben, questions on this?